Well, I'm back from a long break from making videos. Mostly I've just been really busy on programming projects. Part of that will be in another video on my presentation for the recent international workshop on Plan 9. For now though, let's get into ARM processors. So by now we all know what ARM processors are. Pretty much all smartphones use them. They power the Nintendo Switch. Microsoft is putting in serious effort to running on them, and they're becoming a player in the server space. Unfortunately, for the average computer hobbyist, ARM processor is most commonly known as the Raspberry Pi. Credit where it is due, the Raspberry Pi folks made these tiny computers very popular, and they put a lot of effort into making them easy to get into. The downside is they had to put in a lot of effort because the Raspberry Pi is more difficult to work with than most any of the alternatives that now populate the market. For various reasons, Raspberry went with an ARM chip produced by Broadcom. It does things in a very peculiar way, and Broadcom is not very open about what those ways are. However, it's been a while since the first Raspberry Pi was released, and a lot of other companies have entered the market. And a lot of them have better designs with CPUs that are easier to work with. And many of them offer a lot more features than the Raspberry Pi. The downside to this is the drivers and other software often isn't there to really get the most out of them. And too many people are mostly interested in higher level abstract programming projects. Or think that writing low-level stuff is too hard. So here is my effort doing 9 front ports to ARM CPUs. This will mostly cover the Allwinner A64. It's an older chip. It's on par with like a Raspberry Pi 3B, and it's available in a variety of configurations from Pine A64. If you're shopping for single board computers like this, try to get them from companies that really aim to be open source. So open that they can provide data sheets. So in the case of Pine 64 here, they run a wiki about their hardware, and they do provide links to data sheets. So ARM doesn't make chips. They make blueprints for chips, which they sell to companies that actually go out and have the chips manufactured. In the case of the Allwinner A64 here, so it runs 4 of these Cortex A53 cores, and they also bought the GPU from ARM, so it's a Mali GPU on it. These A53 cores also include memory management and interrupt controller. So a lot of the stuff I'm going to be doing here is going to cover kind of the broad category of ARM Cortex A chips. So when it comes to getting these ARM processors up and running at the most basic level, they all largely are going to kind of behave the same. ARM also provides thousands of pages of manuals for booting the CPU, doing memory management, and setting up the interrupt controllers. And as we can see in the manual for the ARM chip, in the section for the interrupt controller, it's the GIC here. So they'll list all the the numbers for all the devices, the interrupt numbers. But at the top here, they just say, go grab the manual from ARM on how to do this. Something of note is that ARM offers a few different interrupt controllers, and the A64 here in particular uses the 400 series interrupt controller. So one of the first things to look at when poking around at hardware like this is the memory map. So this will show the memory locations of various things included with the chip. So right off the bat, we'll need to get access to the Uart so that we can get text output on a serial line and see what's happening when we boot. So there's that there. There's its memory location. Let's see. Oh, there's the eMac. That would be the Ethernet device. Down here, there's the GIC which is the interrupt controller, so that's the memory location for that. And something to keep track of too is where the actual physical memory address for where the actual RAM on the board is. So you need to keep track of that, because this is memory locations where you'd write to make changes to the hardware stuff, but down here is where you'd actually have the kernel and whatever else is going on. So what does this all look like when writing a kernel? So I'm going to be doing a 64-bit kernel. This will be slightly different if you decide to go with 32-bit, and that's fine provided you're using hardware that will never have more than 4 gigs of RAM. And all the software you run on will have to be compiled with 32-bit also. On 9 front, the first thing that runs will be the start function, and that'll be an L.S. I mostly copied this from existing 64-bit kernels for 9 front. Again, the Arm Cortex A53 cores are largely all going to behave the same. So this wave thing here, this I added for doing debugging. They simply, put the memory, value of the Uart into a register, put the character in another register, and then send that character into that memory location. And yeah, that's just going to be the physical location of the Uart, which I found that in the datasheet there. And like the first part where you really need to worry about like how your particular chip is set up is going to be in the initial sort of memory management. So it starts here when you first boot the system. This is where it's going to start. And it's going to run through here. So right off the bat, it's going to make sure the memory management unit is disabled, do some initial setup for the mock structures and stuff. It'll get down to here, and it'll branch to this MMU0 init. So memory management is one of those things that's like now a cornerstone of modern computers. It's one of the things that separates a full-featured CPU from a microcontroller, and then a microcontroller won't bother with any sort of memory management. So initially we have to care about the physical addresses of things, but after this point we'll be dealing with virtual addresses, which will be set up in a sort of directory where the ARM CPU can change a virtual address that we're asking for to the physical addresses for where things really are. And that's initially done here. So here's our MMU0 init. And it's basically, this is just sort of an initial one to set things up. And what it's going to do is basically set up a bit of virtual memory for the kernel. So this is like our actual sort of physical address where it ends. It's actually this whole thing here to a virtual address, and it runs through that thing. Also have one set up for the physical I/O. So that'll be down here. So if we go back to the data sheet here, we can kind of see where our stuff starts and how far it runs. And we'll sort of set it up so that we map out that area of memory and remember to use it for I/O access. So once that's set up, it'll come down here, it'll actually enable it, and then afterwards we're going to have to, if we're going to use the Uart, it's going to have to be accessed through its virtual address. So that's going to, I just have it hard coded for some of these things. So that's what it looks like before, and the way I have mine set up, it'll end up with that as the address afterwards. So once it turns on that, it goes through a couple more things, and then it jumps off to the main function. So again, I mostly copied this from other kernels, because at this point I'm not really doing much other than, you know, messing with the ARM CPU itself. Really the only unique thing so far is the Uart. But we get to the main function. So first off, it's going to do some stuff to set up the mock structure. This next bit here is for the other cores. Since we start off with just one of the cores on and using the first mock number, which is 0, that means that this first run through, this will be false, and we'll just skip it. Uart con's in it here. This is one of the few things that's particular to this chip that I'm doing. So it'll actually call some stuff for the Uart on this board. So this interrupt function here, I commented it out because this is, again, borrowed from another kernel where it used one of the 500 series interrupt controllers that needed some initial setup. So this MP in it here is interesting because this is where the other cores get turned on. So if we jump up to it, we can see here it sort of sets aside that start function from L.S. And note that this for loop starts with 1 instead of the typical 0. And what it's going to do is going to set up the next mock structure. It's going to set it to number 1. Flushes all that out to memory. And then it's going to set up some registers that's going to send over. So this first one here is the actual ARM command to turn a CPU on. It's going to set a CPU. It's going to get the P address, so that's the physical address for where that function is located in memory. And then it's going to use this SM call to actually go run that. And then come back and do sync cycles. Now, core 0 is going to continue on. And this MMU0 clear basically undoes that initial basic MMU setup for the kernel memory, and then goes on to do a proper one. Some of these other previous functions up here, like confident, runs through and tries to figure out exactly, how much memory to allocate for the kernel and for user programs. So once all that stuff's figured out, it'll do a proper setup of the memory management unit, and then jumps off to run the scheduler, and that will continue on with the boot process. Meanwhile, the other 3 cores will fire up, they'll run, they'll go through L.S, starting up at the top here, just like the first core did, and get to main, and then they'll get here, and they'll be not false, so they'll just run through this smaller section of things to set up. So back to the data sheet. So most of the stuff we were dealing with there was mostly just stuff generic to ARM CPUs. So like the details of that command to turn on the cores would be covered in ARM manuals. But part of doing this is that you need some text output to know if what you did worked, and that's done over the Uart console, which is provided by the chip manufacturer. So in this case, Allwinner provides several Uarts. You'll have to check with whoever manufactures the actual board you're working with to see what Uart is connected to what actual physical pins. With this Pine A64 board I have, the pins are on Uart 0. And the datasheet here says that Uart that Allwinner's using is a 16550 compatible. It has a bit more information. And here's all the addresses, the various registers, and then it goes into details on what all the registers do. The 6550 is an old and well-documented design. It's similar to another one called the I8250, which 9front already had drivers for. The driver I'm using was borrowed from another ARM kernel, and then I hacked it up several times as I copied it from one project to another. For just basic text output, all that needs to be done is to put the value of a character into this first register here. If we go back up to the main list here, you'll notice that like the receive and the transmit register are the same one. So for this type of Uart, you know, if you put something into this register, that transmits. If you read from it, that's receiving. You'll want to check with whatever chip you're working with what kind of Uart it's using and whether you have a driver for it. I know that like the Amlogic S905 like has 2 separate registers for transmit and receive. Like the Atheros 9331 has 1 register, but there's a bit in it you have to set on whether you're transmitting or receiving. So this is an important thing to look at if you're going to, you know, boot up a chip, because you know, you want to know if it works, and if something breaks, you want to be able to read an error. So I put together enough stuff in this kernel that it should be able to like boot up and output text. Here's the make file for it. So I'll have to include all the portable stuff. This is for some of the code in the kernel directory here. And when we link it all together, one of the things to keep in mind is that I have this little H6 flag here. This tells the Arm 64 compiler to make this a headerless binary. So don't need a header because it's not going to be running in an operating system. It is the operating system. So sometimes that's important to do, or it might not load. Now I'm going to jump past anything having to do with building U-boot or ARM trusted firmware. Most any board you purchase will already include that. Some boards include it on like an onboard flash storage. Some will expect it on some sort of SD card image. With this Pine A64 board, I'm using a NetBSD card image that includes those. For those unfamiliar with U-boot, it basically provides the functions of the BIOS found in Intel CPUs. So it does some initial hardware setup and then handles what to boot next. And it also includes this little interactive shell here. It can have more or less features depending on how it was built. So there's a couple ways to boot things. Linux kernels expect arguments to be passed to it and some other stuff. But for this simple 9front kernel, I'm going to go with the simplest method of booting. So I've put the kernel on a thumb drive. It saw that when it booted up and sort of initialized the USB system. So I'm going to load off the USB into this memory location, my plan9.ini file. And my kernel already has it sort of hard-coded to check this location and read anything from there like it's a plan9.ini file. And then I'm going to pull in the kernel and put it in this address. So remember the on the data sheet, it said that, you know, RAM started here. So if I tried writing lower than that, I'd actually be, you know, writing into a bunch of registers for, you know, who knows what. All right, so that's loaded into memory. And now I'm going to use what's called the go command, which is very basic. It just tells the CPU to go to a location in memory and just run whatever is there. And there it is. So we can see that the whole thing ran like this. I think that's from that exinit function. This is that like CPU ID one. So this is sort of an interesting thing to note. It's kind of running at like, you know, less than a gigahertz. I'll cover a little bit of that later. There's no networking or anything right now, so the best I can do is run RC, and that will just give me an RC shell with whatever came with the packfs. So there's my memory. And there's all 4 cores. And this section, this little column here in the middle, is actually picking up interrupts, so that's running too. Obviously, it has to be for the Uart to be functioning to pick up that it's receiving characters. Yep, one does not simply read from Mordor. So that's about it for now. I guess I can give a little bit of a preview of what I'm working on next. Whoops. It's gates, plural. Yep. So I wrote this little thing here. So a lot of these ARM chips, since they're meant to go in like phones and tablets and stuff, run off battery-powered devices, have quite a bit of options for throttling clocks. That's why by default this thing is not running at the full speed for the CPUs. And some of the peripherals will also have their clocks turned off. And so my next step was trying to get the networking running, and one of the things I had to make sure was that the clock was on for that. So I noted before there's actually several Uarts, but Uart 0 is the only one that has a clock turned on for it. Like these I2S things here, that's the PCM, that's audio. So right now there's no clocks for any of the audio stuff. Although it does look like HDMI has a clock on. Anyway, I have a version of one of these kernels and a few others up on my GitHub page. I'll have a link down below for that. It's slightly different than the one I'm actually working with here. It's a work in progress, but you can poke around it and get some ideas. And as always, have fun.